Alright, hello everybody, and today we're going to be revisiting the power rule a little bit. So in a previous video, you noticed that the power rule works for all n up here. So for all n that are natural numbers, so 1, 2, 3, 4 and so on. But in fact, n can also be any real numbers as well, and in fact also all complex numbers, but we'll just keep things real for now. So today I just want to go over two examples and prove both of them that they still hold for the power rule. So the first example is the derivative of the square root of x. Well, the square root here we don't really know how to deal with, so let's just write it as the derivative of x raised to the 1/2 power, because something raised to the 1/2 power is exactly taking the square root of it. So now using the power rule, what we can do is just bring this power down to the front. So now we have 1/2 times x, and then we're reducing 1/2 by 1. So 1/2 minus 1 is exactly negative a half. So we have a negative a half up here. And in fact, because we have a negative right here, we can bring this whole x term right here down to the denominator. So we have 1 over 2 x to the 1/2 power, but 1/2 power is a square root. So there you go. That's the derivative of the square root of x, and now we're going to prove it using some first principles. It's not going to be too hard. Alright, so first of all, let's define f of x to be the square root of x. So that means the derivative of f of x, which is f prime, we'll write it like that. That's exactly the limit as some h approaches 0 of, now, what do we have in the numerator? Well, the numerator is just to change the output of our function. So we're going to have some f of x plus h, and we're subtracting f of x to get a small change to the output of our function. So that's rise, and we have to divide it by some run, but our run is just h. Alright, so let's plug all this information into first principles right here. So we have a limit as h approaches 0 of f of x plus h. Well, if f of x, all we're doing to our input is just taking the square root, well then f of x plus h will just be the square root of x plus h, and subtracting f of x, which is just the square root of x itself, and dividing everything through by h. Alright, this looks a bit ugly because we have these square roots everywhere. So I'm going to do a little trick right here. We're going to get rid of these square roots a bit, because I hope you agree with me that if I multiply this by 1, nothing will change. But what exactly is a 1? Well, we can write it as something divided by that same something. And in fact, I'm going to multiply this by the square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. And it might seem that I'm making things more complicated here, but notice one thing. We have this square root minus this square root, and on the other side we have this square root plus this square root. So maybe this rings a bell, because in fact this is just difference of two squares. So I'll just put a quick side note right here. If you have a minus b multiplied by a plus b, that's exactly a squared minus b squared. And this is actually nice in this situation, because we can use these squares right here to cancel out with the square roots. So that's really good. So now we have the limit as h approaches 0 of, well, a squared will just be this square root of x plus h, but squared. But that's exactly x plus h, because the square roots and squared will cancel out. And now we have to subtract b squared. But b squared is exactly the square root of x, but squared. So that happens to be x itself. And now we have h. Let's combine these two denominators together. So we have h square root of x plus h plus the square root of x. Alright, and you may notice that this x and this x will cancel, and another cool thing happens. This h and this h will cancel, and all that we're left with is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And notice that h is not alone on the denominator, so we can in fact directly plug h equals 0 into here, because as h gets smaller and smaller and smaller, well, inside the square root here will just become just the square root of x pretty much. So now pretty much all we have is 1 over the square root of x plus 0. So as h gets smaller and smaller, it's just going to turn into 0 plus the square root of x. And what is that? That's 1 over the square root of x plus the square root of x. And that's exactly 1 over 2 times the square root of x, as we were expecting. So in fact, the power rule also works for fractional powers as well. Alright, so now for the next example, we're going to take a look at the derivative of 1 over x, so the hyperbola. We don't really know how to deal with this 1 over x, so again, we'll rewrite it as being the derivative of x, but raised to the -1 power, because that -1 just brings that x to the denominator. Alright, and just applying the power rule directly, bring this -1 down to the front. What we're going to get is -x, and then now we have to reduce this power by 1. So -1 minus 1, that's exactly -2. So now because we have this negative here, this x can flip down to the bottom to get a negative, something over x squared, and that something is just 1. So this in fact is the derivative of 1 over x. Alright, so now for the more rigorous proof of this by using first principles. So first of all, let's define our function f of x to be 1 over x. Well, f prime of x, the derivative of f of x, is the limit as some h approaches 0 of the rise, which is the difference of our 2 points, over the run. So rise over run, that's gradient, which is pretty much the derivative. Alright, and just plugging this information into here, we're going to get the limits as h approaches 0, and now f of x, all we're doing to our input is just taking 1 over the input. So the input here is x plus h, so f of x plus h will just be 1 over x plus h. And now we're subtracting 1 over x, which is the function itself, and we're dividing everything through by h. Alright, this doesn't look as bad as the square root case, because we just need to do some algebraic manipulation. But first of all, what we can do is combine these two fractions together. So first of all, what we have to do is get them on the common denominator. So if we multiply this left fraction here by x over x, so multiplying that by x over x, that's not going to change anything. And multiplying this right fraction by x plus h over x plus h, because notice these two denominators are the same now. So now we have the limit as h approaches 0 of, now we just combine the two numerators, so x minus x plus h, all divided by x times x plus h. And in fact, we're dividing everything through by this h here, but because we're dividing denominators, we can just multiply the two denominators together. So now we just have a h here as well. So now let's expand out this bracket. It's just going to be negative x, and then distributing this negative will give us negative h. Alright, and this x and this negative x will cancel, as well as this h and h right here. And now all that we're left with is the limit as h approaches 0. And don't forget about this negative right here. We have -1 on top, and x plus h. And now what can we do from here? We can expand out this bracket a little bit to be the limit as h approaches 0 of -1 over x squared plus x times h. And notice that h is, again, not alone on the denominator, so we can directly see what happens as h equals 0. So as h gets smaller and smaller and smaller, this term right here will just pretty much disappear off to 0. And what we're left with is -1 over x squared plus 0, because that's what this term turns into. And indeed, we do get, in the end, -1 over x squared. So the power rule also works for negative powers as well. So that's pretty much it for this video. This is just an extension of the power rule to being all real numbers. So the power rule even works for irrational numbers. So if you have, say, the derivative of x to the pi, well, you just bring the pi down and you get x to the pi minus 1. So that's pretty cool. So yep, that's pretty much it, and I'll see everyone next time.